Humans are decent at physics. We can create equations to accurately describe the world around us, but when it comes to actually putting them to use, we are painfully slow. You know what is great at doing calculations fast? A computer. Welcome to the wonderful world of physics engines. A physics engine is simply any type of software that approximately simulates a physical system. Three main types of physics engines exist. The first is a rigid body simulation. These simulate the movement of objects acted upon by forces. The most notable feature of this kind of simulation is that the objects are rigid. This means that they do not deform. As such, the movements of the objects are governed by the laws of kinematics and Newton's laws. These are the most simple to simulate. The second type of physics engine is a soft body simulation. These are like rigid body simulations, except the objects do deform or change shape. This massively increases the complexity of the simulation, so they are often only visually plausible, rather than completely accurate to what would happen in real life. The final type of physics engine is a fluid simulation. As the name suggests, these focus on simulating the movement of fluids, such as water or air. These are often used to create visual effects in films and games, and are also used in engineering to make sure that things like vehicles are as aerodynamic as possible. Furthermore, there are two classes of physics engines, real-time and high-precision. Real-time engines use simplified calculations to simulate physics in real time. These are most commonly used in video games, as speed is more important than accuracy in these cases. High-precision engines calculate physics much more precisely, but take much longer. These are used by scientists and engineers and in computer-animated movies to create realistic effects. In fact, the first physics engine ever made was of this type. One of the first general-purpose computers, ENIAC, built in 1945, was used as a simple physics engine. The US military used it to calculate the trajectory of artillery shells, and it even accounted for wind. But enough talk about the different types of physics engines. What does it actually take to make a physics engine? For my personal physics project, I made an impulse-based, rigid-body physics engine. In this type of engine, there is a two-step process in making the physics work. The first step is detecting a collision, and the second step is applying an impulse to the objects involved to resolve the collision. Let's first focus on collision detection on two simple shapes, circles and axis-aligned bounding boxes, or AABBs, which is a fancy name for a rectangle that does not rotate. In a physics engine, there is more to collision detection than simply finding out if two objects are touching each other. There are two additional things we want to know when checking for a collision. The first is the collision normal. This is the vector which contains the direction in which the force, or in our case impulse, will be applied in. For example, a ball sitting on the ground has a vertical collision normal, and two boxes sliding into each other have a horizontal collision normal. Note that this vector always has a length of 1, as we only need it for its direction. The second thing we need to find is the penetration depth, which is how far the two objects have moved into each other. Let's first go ahead and find these things between two circles, which is by far the simplest case. To find if a collision has occurred and the penetration depth, all we need to do is take the sum of the radii of the circles and subtract the distance between the centers of the circles. This finds the penetration depth. If the penetration depth is greater than 0, then a collision has occurred. The collision normal is also easy to find. We simply create a vector from the center of one circle to the center of the other. Then we normalize the vector, which means rescaling it to a length of 1. Just like that, we have all the data about the collision that we need. Two AABBs is a bit more complicated. To check for a collision, we check if the left edge of one box is to the right of the right edge of the other box, if the top edge of one box is below the bottom edge of the other box, and so on. If none of these occur, then the boxes are colliding. To find the penetration depth, we check each face of a box, find how much has penetrated the other box, and then pick the lowest non-negative number. Finally, we use a line tangent to this face, known as the face normal, as the collision normal. A circle and AABB collision is quite interesting. First, we find if the circle is closer to a face of the AABB or to a corner. Then we simply have to deal with either a circle-to-point collision, which is like a circle-to-circle collision with the point being a circle of radius 0, or a circle-to-line collision. In the case of a line, we simply have to use the distance from the circle to the line to determine whether a collision has occurred and the collision depth. The collision normal is simply the face normal of the chosen face. So our objects have collided. Now what? Well, we have to apply an impulse to push them apart. In physics, an impulse is simply a change in momentum. This means we will change the velocity of the colliding objects instantaneously, according to the equation delta v equals j over m. Of course, this isn't 100% realistic, as acceleration does not occur instantly in real life, but it greatly simplifies calculations. Another thing we know about is Newton's third law of motion, which states that for every action there is an equal and opposite reaction. This means that for an amount of impulse we apply to one object, we must apply an equal and opposite impulse to the other object. Finally, we have already calculated the collision normal, so we know the direction to apply the impulse in. All that is left is to find the magnitude of the impulse. This can be found with the following formula. But why does this work? Let's start with the relative velocities of the objects. VAB equals to VA minus VB. By subtracting the velocity of object B from object A, we get the relative velocity of A relative to B. Next, we take the dot product of both sides with the collision normal vector, resulting in VAB dot n is equal to VA minus VB dot n. The dot product is a function on vectors that is maximized when the angle between the vectors is 0, and 0 when the angle between them is 90. This is useful for our collision calculations as it gives us the relative velocities of the two objects in the direction of the collision. So, if two objects collide head-on, the dot product is maximized, and if they just skim each other, the dot product is 0. Next, we need to take into account elasticity. Newton's law of restitution states that V2AB is equal to negative E times V1AB, with E being the coefficient of restitution, which is between 0 and 1. If the elasticity is 0, the relative velocity after the collision will be 0, and if the elasticity is 1, the relative velocity will be the same, but in the opposite direction. Next, the formula that defines how much an object changes in velocity is the equation delta v equals to j over m. By taking into account the direction of the impulse and adding the initial velocity of the object, we get v2 equals to v1 plus j over m times n. For the objects a and b, we get the following two equations. Finally, we have everything we need to derive the equation. First, taking into account elasticity, we get the following equation. Next, we can substitute in the previous two equations for v2a and v2b. This gives us this equation. Next, we distribute the dot product on the left side, giving us this. Since we know that VAB is equal to VA minus VB, the left side of the equation simplifies to this equation. Finally, we can solve for j. N is a unit vector, so its dot product with itself is always 1. Therefore, we can ignore this term. And just like that, we can figure out the impulse of a collision with only parameters from before the collision. The last step to turning this into a functional physics engine is simply to move objects every frame according to their velocity, and immovable walls with infinite mass. With this put into code, we now have a neat little physics engine. It can handle balls bouncing around nicely, as well as blocks. Intriguingly, it can also calculate pi. With a block a power of 100 times more massive than another, a wall, and perfectly elastic collisions, the number of collisions that occur are the first few digits of pi. This is really neat, as it is quite possibly the most elegant yet least efficient method of calculating pi ever created. There is a problem with this version of the physics engine, however. Due to floating point errors, objects can sink into each other. This is where the penetration depth comes in. We simply move objects a percentage of the penetration depth away from each other along the axis of collision. With that done, the basic physics engine is complete. Let's implement friction into our engine. To do this, we simply apply another impulse tangent to the collision, which is 90 degrees to the first impulse. How large it is proportional to the first impulse, as well as the coefficient of friction. We make the value of the friction impulse equal to this, and also make sure that the friction impulse is limited to stopping the object, rather than making it move in the opposite direction. With that, friction has been put into the simulation. Next, how about making the objects rotate? To do this, first we must improve our collision detection. We need to find one more piece of information, the support point. This is the point at which the collision has occurred. I won't talk about the specifics in finding it, but if you want to know more, there is further reading on my website. Next, we will implement torque. Torque, also known as a moment, is the rotational equivalent of linear force. It is the cross product of radius and force. As we are making an impulse-based engine, we will instead instantly change the rotational velocity of the objects. Therefore, we will use the cross product of radius and impulse instead. As rotating an object will take some energy, our impulse formula will also have to change, becoming this. Friction will also apply torque. With that, the physics engine is finally complete. As a next step, I could rewrite the code in a faster language as well as optimize it. I made my program in Python, which is easy to use but also very slow. As such, simulating lots of objects creates tons of lag. As for the real-life applications of physics engines, there are many. As mentioned at the start, they can be used in video games and animated films to create realistic effects. They are also used by scientists and engineers to test out concepts without having to build a model in real life. Finally, a new use for physics engines is training artificial intelligence. For example, a robot could learn to walk in a simulation, and when the robot is built in real life, it can walk immediately. Anyway, I hope you've enjoyed this exploration of physics engines. Thanks for watching.